Good morning. This question is from NCRT. Now, before we start solving this numerical, we will first cover these topics which you see in front of you on the slide. All these topics, once you understand them, you will be able to solve this numerical very easily. So, therefore, go through each of the topic, develop your concept, and then go and do the numerical solution. Do not watch the numerical solution directly because you will learn nothing. It's a waste of time. This is the only channel in the country which is giving complete explanation and then solving the numerical. Okay, let's move to the topic discussions now. Thank you very much. Nucleus. Now, nuclear physics has a lot of units. We will start this discussions with the concept of units in nuclear physics. So if you read this question, you're supposed to find the Q value and stuff like that, but I'll come straight to the point. Please see this. You can see this U, right? So let us start with basics, that what are the units that are used in nuclear physics. So we're talking about units used in nuclear physics. Okay, whenever we study the concept of nucleus, we must know the units that are used in it, right? So nuclear physics, right? So I'm drawing your attention to U. You see these U, right? This U is also called as atomic mass unit. Okay, so this is one atomic mass unit, and this is equal to 1.66 into 10 raised to power minus 24 grams. Okay, I am not going into derivation. I am straight away telling you what it means. And how do you get this? What you do is, so this is one atomic mass unit. You use Einstein's formula of E is equal to mc square, and you put this value, mass, which is this much mass. You can see this mass, 1.66 into 10 raised to power minus, I'm going to convert this to kilograms. So I will divide it by 10 raised to power 3. So this becomes 27 into 3 into 10 raised to power 8 whole square is equal to, and what I will do is, although the answer I'm going to get this in joules, I will convert the joules into million electron volts, and I will get a figure of 931 million electron volts. I'm not doing derivation. I'm telling you the units right now. Okay, what is that you learned? That if you have one U as your mass, which is this much, and you convert it to its equivalent energy, right? The rest mass energy using Einstein's mass and energy equivalence formula, one atomic mass unit becomes 931 million electron volts. So when you see U, okay, they're referring to an energy of 931 million electron volts. This is the first thing you must understand, that whenever you're solving the questions of nuclear physics, so this has to be memorized. Memorize these two things. Memorize the mass and then memorize the equivalence, which is 931. Very useful concept. Okay, so we will develop the concept of this question, and gradually I'm going to tell you the basics alongside. So we will develop both the concept and the numerical. All right, let's move to the next topic. All right, so the second thing you must understand is what is a nuclide. Okay, what is a nuclide? Okay, and if you go back to this question, see this question, you can see 226 and 88. How do you read this, right, in a radium scenario? We will solve this question, don't worry, but listen to this very carefully. Any nuclide is written like this. So you have the atomic mass number, which is the sum of the number of protons plus number of neutrons in it. Then there is a atomic number, which is the number of protons, and then there is n, which is the number of neutrons. Okay, n. Generally this is not written, and you will find x, a, and z mentioned. This will tell you number of protons. Okay, as simple as that. So you can always find out the number of protons, and this gives you the number of neutrons and protons. If you subtract these two, a minus z, you will anyway get the number of neutrons. So you should be able to read a nuclide pretty well. A nuclide tells you, generally when you write a nuclide, it tells you the number of protons inside it, the number of neutrons inside it. And the third thing, which is associated with the concept we have studied, a nuclide is also associated with the how much the content of energy it carries. I'm not going to go in detail of this, the content of the energy it carries, but we will certainly develop this later. Now you also understand how to read a nuclide. Let's move to the next concept. Gradually we are developing concept basics, and then we will finally solve the numerical. All right, so third thing you must understand when you do these questions, and I'm still not talking about Q and kinetic energy. Do you see the word alpha particle and alpha decay? So I will briefly tell you what exactly is happening. I have still not touched Q and kinetic energy. You have radium which is given to you, and this radium obviously has a mass number and atomic number which you've already studied, 226 and 88. And this radium now undergoes a alpha decay. So we will write the nuclear reaction. So 226, 88. What are you studying? It undergoes an alpha decay. Okay. Whenever anything goes through an alpha decay, for example, this is your situation A and Z. Okay. So these are the number of nucleons. This is the number of protons. What is nucleons? Nucleons is sum of protons and neutrons. So it undergoes an alpha decay. The whole focus is alpha decay. It becomes something Y, and a alpha particle is released, right? Now, when you have to, if there is a situation of alpha decay, this is what you need to do. A subtracted by 4 and subtract Z, the number of protons, by 2. This equation which I have written shows you an alpha decay. I hope this is clear. Alpha, incidentally, is helium 4 2, which is charged. I hope this is clear. This is another thing you must understand, which is alpha decay. Let's move to the next topic now. Right. So now let's develop the concept of Q. Okay, Q of a nuclear reaction. We're dealing with nucleus. Now we will write a reaction, and then we will study what exactly is Q. So you can see the example of radium, which is 226, 88. It breaks, and what it becomes is, we don't know what it becomes. Forget it. So it becomes some X, and we know 226 minus 4 because of what? Because this is a situation of alpha decay. Alpha decay I have already explained, minus 4, and you will write 88 minus 2 here, and an alpha particle which is nothing but helium with a 2 plus charge. We don't have to worry about the charge. This is basically a alpha particle. Okay. So this is a nuclear reaction, like you have in chemistry, chemical reaction. This is a nuclear reaction where a lot of nucleuses are being shown. This is also some nucleus we don't know, and we don't need to worry about it. So I will just write it. So 226 will become 222 and 88, and this will become 86. And then of course helium or alpha particle. Okay, I can write this as alpha particle. It's an alpha decay. This is radium 226 and 88. All right. Now let's discuss what is the Q of the reaction. Okay. The first thing is, in the case of this scenario or any other scenario, whenever a nuclear reaction happens, the Q, okay, before you write the Q, you have to write what is the mass on the left hand side. Now this is the place where the whole story starts, right? And then this, and this is also known as, some call it like a mother nuclei, the mother of all, right? So this is your mother nuclide, and then it produces a daughter nuclide. Okay, and these are the alpha particles that get released. Okay, so the mother nuclide gives you a daughter nuclide. What you need to worry about now is how do you write the mass of the left hand side and the right hand side. Okay, so one is that we talked about E is equal to mc square. We had written about it, right? So this is one thing you must understand. We already have understood this, wrote about this. So second thing which is associated with any nuclear reaction, and I will give you a diagram to help you understand, is the kinetic energy. So whenever you see a nuclear reaction, something like a radium breaking into some another nuclide and a helium in the form of alpha decay. So there are two energies you have to always look at. Any nuclear reaction has to be seen with respect to two quantities. One, the rest mass energy, which we studied, right? 931 million electron volts. So that is another form of energy where the mass is being converted to equivalent energy, assuming the mass moves with speed of light, the Einstein formula. And then you also need to look at the nuclear reactions from the lens of kinetic energy. So whenever you see a nuclear reaction, immediately think of two energies. One, the rest mass energy, which is like this, mc square, and the second energy always think about is kinetic energy. Why do you need to think about it? Because any chemical reaction, nuclear reactions have the left side, which is the reactants, and then on the right hand side, what they produce is the products, right? So left hand side is all reactants, and then right hand side is all products. What you do is, and then you know that there is a law of conservation of energy. You can have mass getting converted into energy, but you cannot lose energy in a nuclear reaction. It stays conserved. So what you do is you see the situation on the left hand side of a general situation, and you say, okay, my left hand side is some kinetic energy on the product side, which is, you can write product or you can write initial, and I have some mass energy on the left hand side, which is the mass of radium nuclide. So you can write this as mass of radium nuclide, and you can write it as mc square, and or you can write it as the initial mass. Okay, so this is the left hand side of a general equation. I'm using the example of radium. It can be anything, and this could be the kinetic energy of radium itself. In our question, there is no kinetic energy of radium given to us, but you may be given, right? And now the left hand side energy has been written, the kinetic energy has been written, the rest mass energy of left hand side has been written. I'm using the word initial. Now write the same thing for the product, because the energy has to be conserved. So write the kinetic energy of the daughter, which is like, right? So let's say it's kinetic energy final of the daughter. Then you can write the mass, equivalent mass energy of the daughter, the rest mass energy. So daughter is nuclide is, and you can write it as, I'm using F to show you final on the right hand side, okay? And this shows you it is the daughter, right? The daughter is here. And then of course you have an alpha particle. So the kinetic energy of alpha particle, it is also final because it is on the right hand side. I can use the word product also, plus write the rest mass energy of alpha particle. So this is rest mass energy, and this is also on the right hand side. So final into c square, right? So you have written two energies. Left hand side has a kinetic energy of the radium. In our question does not exist. We have written the rest mass energy of radium. Then on the right hand side, we have written that we created a daughter nucleus. We have written the rest mass energy of the daughter. We've also written the kinetic energy of alpha, and we've written the rest mass energy of alpha, right? So you can see the whole focus, the thought process has to be kinetic energy and the rest mass energies on the left hand side and right hand side have to be equal. Why are we studying this? Because we finally want to understand what is the Q of the nuclear reaction. This is what we want to study. But you must know this law of conservation of energy that gets applied in the form of kinetic energy. If you see the question also talks about what is the kinetic energy of this alpha particle, right? And I will tell you where this whole thing is coming from, what exactly is happening, etc., etc. But first, basics, very basics, have to be understood. This is like a revision of your chapter also, and then you're solving a numerical parallelly. You're revising the chapter, you're also solving a problem. I'm not solving the problem in 30 seconds or 1 minute because it teaches you nothing, right? It's a waste of time just seeing a solution without understanding anything. All right, let's move forward. Now that you understand there is something called as in rest mass energy, a kinetic energy, and a law of conservation of energy has been applied to a nuclear reaction, just like a chemical reaction exists. Now let's further develop the concept and move to the next topic. All right, so the next topic is the topic of binding energy. This is very useful when it comes to developing the concept of Q value of nuclear reactions. Okay, and let's discuss the binding energy now. It's important. All right, so how do you define binding energy? So if you notice a reaction, a nuclear reaction happens, and this is your parent nucleus, and this is the situation. And I will give you a very simple example. You have a daughter nucleus that gets created, and it's alpha decay. We will keep it simple. Simple examples which you understand what is an alpha decay, -2, and then there is an alpha particle that comes out. If you were to find the binding energy, okay, binding energy of a nuclide, binding energy, okay, of a nuclide, how do you do that? The binding energy of a nuclide is defined as the difference of energy of individual nucleons. So what you do is take, for example, this, okay? How many protons are there? You know the number of protons. Calculate the rest energy of the protons in X. So let's say the number of protons is Np. This is the mass of the protons, right? And multiplied by C square. So I'm referring to individual protons. All the protons put together, this is the mass. Okay, the rest mass of all the protons converted into rest energy. So this is, and then you have how many neutrons? So we will write the number of neutrons. Let's say these are, so this is the mass of all the neutrons individually in X. So I'm writing the X only. Okay, we are not writing this, none of this. We're just referring to the X. So this is the total rest mass energy of the nucleons inside X. Rest mass energy of the nucleons inside the nucleus of X. Now calculate the mass of X nucleus. Okay, so let's say the mass of X nucleus is mx, and again converted to mass energy. So now this is the rest mass energy of nucleus of X. So you have done two things. You've calculated the individual masses of the protons and neutrons, multiplied it with C square, obtained the rest mass energy of the nucleons. Then what you did was you went to the nucleus, calculated the rest mass energy of the nucleus, subtract these two energies. So subtract the rest mass energy of all the nucleons and then calculate the rest mass energy of the nucleus And what you get now is the binding energy of that nuclide, right? So the individual masses of MP, if you calculate the mass of all the protons and all the neutrons, you will find that individually, when you calculate the value, it comes out to be greater than mx, right? So which means this particular nuclide, okay, is stable because when the protons and neutrons came together, they lost a mass. Mp plus Mn minus Mx is the mass they lost. Okay, and if you multiply it with c square, you get delta mc square, which is called the rest mass energy due to mass defect and known as the binding energy. This is called the mass defect. And there is a reason why you're learning binding energy to calculate Q, because I'm going to tell you something very, very interesting to be able to solve these numericals in a very fast manner. So I hope the what the key words you must remember are that there is a rest mass energy of the nucleons, there is a rest mass energy of the nucleus. The rest mass energy of the nucleons is always greater than the rest mass energy of that nucleus. That difference is called as the binding energy, and it occurs because of the mass defect. And when I told you that any nuclide has to be identified with the help of three quantities, nucleons in it, which is proton and neutron, and the energy content inside it, this is what I was referring to, the binding energy of the nuclide. So if you supply this much energy to X, the protons and neutrons will get separated, right? So that is another definition of binding energy. Let's move to the next concept. All right, now let's define Q. So we have done so much preparation to understand Q. All what you learned so far will get utilized in understanding what is Q. So let me give you the exact situation which I told you. I will help you with the help of a diagram. So let's see, you have a situation like this where you have a nucleus. Okay, this is a nucleus, and then what you have is a small body like a neutron, right? A neutron comes and hits some element. This could be anything, right? So this is your a neutron, for example, can be anything, and this is your parent nuclei. Okay, parent nuclei. This particle, which could be a neutron, you bombard it with neutron, comes and strikes the parent nucleus. There is a collision that happens, and then, for example, you have after the collision, you might have studied momentum and all that. So something very similar is happening now. And now what is happening is, so if this is your X, this is your capital X, you have this as the daughter nuclei, and then some smaller nuclear. For example, this could be a smaller one like hydrogen that gets released. These are just examples. This could be a neutron. Okay, as an example, I'm just telling you. Okay, we have to write it like this. All right, I hope this is clear. So this collision happens, and you can see the daughter nucleus is here. Daughter nucleus. Now, every question which you have, which is pertaining to Q value of a nuclear reaction, where nuclei interact with each other. So you can see this is a nucleus of X getting converted into Y. So this is like X plus X becoming Y plus Y. Okay, I hope this is making sense to you. This is some kind of nuclear reaction which is happening. Now, if you think if the velocity of this neutron or a small nucleus is Vx, say this is at rest, so capital Vx is equal to 0. The velocity of this is Vy, and the velocity of this one is Vy. Now, what is Q in terms of the kinetic energies? I told you Q value is always calculated in two terms. One is the kinetic energy involved in the nuclear reactions, and the second is, of course, the rest mass energy, which is like EMC square, right? These are the two ways you calculate. And I told you about the law of conservation of energy also. Energy will remain conserved, but it will appear in different formats, okay? Now, when the Q value of the reaction is talked about, it is generally the energy which is released during the nuclear reaction or absorbed during the nuclear reaction. All right, so when the energy is absorbed in a nuclear reaction, what does it mean? See, some nuclear reactions can only happen, some nuclear reactions require energy, okay? They require energy. For the nuclear reaction to happen, they absorb energy. So this is the second situation of absorption of energy, okay? But in some nuclear reactions, the energy is released, okay? So you must understand that when I say Q, you can have two situations, absorption or the release. Now let's talk about the mathematical expressions and the formulas required to calculate Q. One important point which I want to add to what I just said is there is another way to calculate the Q value, and that is the use of binding energy. This method is very popular because it is some kind of shortcut, okay? It makes your life very simple. Although we can solve it using the kinetic energy, the rest in mass energy, and the binding energy, but still binding energy is one of the easiest way to calculate the Q value. Let's start with the first method of kinetic energy. So you have to refer to this particular reaction. Q can be calculated using the kinetic energies of the various nuclei involved in the nuclear reaction. So if you notice the first one, if you have the kinetic energy of the first, I'm referring to the equation number one known to you, and then the kinetic energy of capital X. These are some kind of reactants, right? So they're reacting with each other. It's a nuclear collision, but I'm calling it reactant, okay? And then you subtract the kinetic energy of the products, okay? So the daughter nucleus side, the right hand side of the nuclear reaction after the collision is what I'm referring to, and kinetic energy, right? This is called as the Q value. So kinetic energy is one format. The second format, which is used generally, is you calculate the rest mass energy of the left hand side, which is the calculate the mass of the X. I'm referring to the left hand side, and then mass of capital X, the parent nucleus, C square. Like we understand this pretty well. We studied about 931 million electron volts rest mass energy, and then of course my and m capital Y C square. Okay, there is no hard and fast rule. You can reverse the equations. What is more important is that you're able to understand whether the Q is positive or negative, and then be able to explain what does a positive Q mean, what is a negative Q mean. And the third way you calculate the Q value of a nuclear reaction is using the binding energy. So calculate the binding energy of the X, then calculate the binding energy of capital X, and then subtract the binding energy of the right hand side after the collision. Okay, so this is BY, This formula is very popular because a lot of calculations get cancelled out, and it becomes a very short way to do that, and you just need to worry about the mass defect. All right. So if you see this, this is third way. So method number 1, formula number 2, and formula number 3 is what you need to learn to be able to solve Q. We will just some additional information. The Q is also called as disintegration energy. Okay, this is another name you will see for Q. For example, if a reaction happens where X is the parent nuclei and it gets converted into a daughter nuclei and maybe a small nucleus which comes out. If you were to write the disintegration energy of this reaction, so this could be your alpha decay of radium. Okay. The way you express Q now is you calculate, what you do is you write the atomic mass unit is the unit now of X, and then subtract the atomic mass units for Y and get this, okay, and you multiply this with C square. You remember 931 million electron volts. So if this is your some kind of the rest mass energy difference, will be simple. So if you see the disintegration energy, this is the way the disintegration energy, and I've told you this is one of the methods, good one, to solve it. Binding energy is probably the easiest one because it is completely, if you do the calculations with the help of binding energy, you just worry about the mass defects, and the binding energies only need to be subtracted. I hope so what you learn now is there is a new terminology called this disintegration energy. If you see the word disintegration energy, do not be scared. It is same as your Q value of the nuclear reaction. In terms of terminology, sometimes X is also called as a target because a beam comes and hits a target. Okay, the target is also known as the parent nuclei, and on the right hand side, which I repeatedly refer to as the reactants, these are the products. So this is these are the jargon or the points you must know, that in some questions you will see the word target, parent nuclei, one and the same thing, and then you may see a word like beam of, some particles come and strike the parent nucleus and it gets converted into a daughter nuclei and a smaller daughter nuclei, right? Now this is very, very important, okay? Now what we've studied so far is that Q is the energy released in the nuclear reaction, or it is absorbed in the nuclear reaction. One thing I told you is we will discuss what happens to what is the source of Q, right? What is the source of energy released and why some reactions need energy absorption. This needs to be understood, and I talked about that. We will discuss this later about energy getting transformed from one state to another state. The law of conservation of energy will hold good, but the energy keeps on changing. Now, assume a reaction where you have Q which is greater than 0, okay? These are known as exothermic reactions. Exothermic reactions, okay? The quality of this reaction is that the binding energy, okay, the binding energy, and the formula used to calculate binding energy, not the binding energy, but Q being calculated using binding energy. And then we have also studied that rest mass energy formula to calculate the Q. If the binding energy or the rest mass is getting converted to kinetic energy, okay, it's getting converted to kinetic energy, this is a situation where Q value is positive, okay? As an example, if you have this example of radium, right? You have radium 226 and then 88 is getting converted into something which is 2, 2, 2. You already understand this, 86 plus an alpha particle. Then this alpha particle, which is coming out from the collision, has very high kinetic energy. So this has very high kinetic energy because it is light in mass. Okay, after the collision, and you can go back to the that part of the video where I've drawn this diagram where the two nuclei strike. This is your beam, and then this is your parent nuclei. After the collision, the you know the daughter nuclei goes here, and then, for example, the alpha particle goes in this direction. If this happens, alpha particle carries most of the kinetic energy. So if in a reaction you find that the binding energy or the rest mass energy, okay, are getting converted into kinetic energy, those reactions are exothermic. And so you understand, right? The source of kinetic energy is the binding energy and the rest mass energy. Okay, but there are certain reactions where Q is less than 0, and these are called as endothermic reactions. Okay, now in these reactions, the kinetic energy, okay, the kinetic energy gets converted into the binding energy. So these reactions absorb energy. Okay, that is the most important thing. For the nuclear reaction to happen, sometimes you need to absorb energy. They absorb energy from this source of kinetic energy. That kinetic energy gets converted into binding energy or the rest mass energy. Okay, in these cases, Q is always negative. So this is very important point. We have studied so much of nuclear physics only to finally reach the stage where we're able to really understand what's happening. Right? You studied kinetic energy, you studied rest mass energy, you studied binding energy, right? And you studied some parts of the the terminology. You studied what is it. We started from very basics, and now we have reached a stage where we have started linking all the terms which are given in the question. If you read the question very carefully, you have kinetic energy, you have Q, you have atomic mass unit, and so many other things. We have defined almost everything we could in this question. Let's move to the next topic, which is also very important, not really relevant to the question, but you must understand that also, because a lot of times students don't know a nuclear reaction happening where some of the stuff which happens is not only pertaining to kinetic energy but also to momentum. I did mention momentum earlier. Let's move to the next topic and have one more concept in your mind for the questions pertaining to nuclear reactions. Thank you very much. All right, so you must understand that the nuclear reactions, for example, we are studying radium, we are studying 22688, and there is a alpha decay. An element called as radon gets built. I've been writing this as X, but it's actually radon. So this is 86, this is 222, and this is alpha decay. So alpha decay is there, right? So this is what we are studying in the NCERT question. All right, now what you must understand is, so I've told you law of conservation of energy holds good. Law of conservation of energy is true, and you have already studied that the mass energy or the binding energy is getting converted to kinetic energy, or the kinetic energy is getting converted to the mass energy and binding energy, depending on what is Q, right? Q is greater than 0 or Q is less than 0. Another conservation law that you should know when you study these questions is the law of conservation of momentum. Law of conservation of momentum. Okay, and sometimes in examination, although not in class 12, but in entrance examination, they give you a nuclear reaction, and the nuclear reactions generally happen in isolation. There are no external forces involved, it's all internal. And therefore, in those questions, you also need to apply the law of conservation of momentum. Just be very careful that, so for example, in this case, although we have not been told what is the momentum of radium or what is the momentum of radon, the assumption is whatever momentum is there. For example, this is at rest, it's an alpha decay, so the initial momentum is zero, and then there is a momentum which is between these two. So some momentum is carried by the radon, so this is a momentum of the radon atom, and then there is a momentum associated. Oh, sorry, let me use the word P because that is what momentum looks like. So P, and then you have some momentum associated with alpha. In this question, if you notice, they're asking you the energy of the alpha particle, the kinetic energy. Right. So once you write down the equation of momentum, you can find the kinetic energy also. Let's see the method to be used. So the mass of Rn plus, sorry, into velocity of Rn plus mass of alpha particle into velocity of alpha particle is equal to 0. This is your law of conservation of momentum. And then and we have assumed the parent nuclei is at rest. So use this, and what you can do with the help of this is, you can find the value of Vrn is equal to minus m alpha v alpha divided by m Rn, right? So now you know the velocity of the daughter nuclei, right? And you know the kinetic energy. So you know the disintegration energy which you found so far. What you do is you write it as the kinetic energy which is split between Rn, okay, and it is split between the alpha particle. So you have whatever energy got created, which was kinetic energy, right? The Q energy which got created has got converted and split between the kinetic energy of Rn and the kinetic energy of alpha particle, right? So we are referring to the daughter nuclei and the alpha particle, which is the alpha decay. You can calculate Q, which we will do shortly with the help of the various formulas we have learned so far and the concept. So the whatever energy is getting released is getting consumed by way of kinetic energy. But most importantly, if you notice the concept here, if you don't understand law of conservation of momentum, you cannot solve this class 12th problem. And therefore, I repeatedly tell everyone the class 11th needs to be strengthened. Otherwise, you cannot. All right, so let's continue to solve this. We will find Q using the various formulas like binding energy. I will tell you how. And then we know half m Rn. Let's substitute the value here, which is minus m alpha v alpha divided by m Rn, which is coming from here, square plus half m alpha v alpha square. Okay, so now if you notice this equation, you can write this as half m Rn m alpha square v alpha square divided by m r square plus half m alpha v alpha square, right? So you can see this goes away, and what is that you're left with? You're left with half m alpha square v alpha square plus half, and there is of course an mr here, half m alpha square v alpha square. If you notice, I will just show you, and this is where a bit of mathematical knowledge is required. You get to this point of half m alpha v alpha square. So I'm just taking one m alpha out, multiply by m alpha into m. What is this? This is m, and this is half m alpha v alpha square, right? So do you see this is the kinetic energy of the alpha particle. So kinetic energy of the alpha particle, and m alpha divided by m Rn plus 1, and this is equal to Q. Now if you notice this, the Q has been calculated already, right? And we know the various methods such as mass defect and rest mass difference which we use, okay? And we will shortly solve this numerically. So far what we're doing is basics, right? So this is known to us, m alpha is known to us, mRn is known to us. We will be able to find the kinetic energy of the alpha particle. So with the help of this formula, find the kinetic energy of the alpha particle. Okay, the key point you must remember is when the energy is released, the disintegration energy or the Q, in a endothermic, in an exothermic reaction, when the energy is released, that energy is getting converted into the kinetic energy of the all the nuclei that are getting produced, and we have to use the law of conservation of momentum to be able to do that. Let's start solving this question numerically now and complete the solution. All right, now finally the solution, right? So you know Q is given by the mass of, okay, this one. If you notice, right, the energy has been released. So you will write mass of Ra minus the mass of the products, which is Rn, and the mass of alpha particle, right? And then you will obviously you have to convert this. Everything is in U, atomic mass units, right? If you multiply it by 931 million electron volts, which is energy per unit atomic mass, one atomic mass unit, one AMU gives you 931 million electron volts, right? So what will be the energy associated with this? Let's start substituting the values. 226.02540 minus 222.01750. And just to tell you, the value of mass of alpha in atomic mass units should be known to you. The atomic mass of alpha particle is 4002603. Okay, just put a dot here. So if you notice, what we have used so far is this is the parent nuclei, this is the daughter nuclei, and then of course alpha decay has happened, right? So the equation looks like you have the Ra 22688 decays to Rn triple two. It's an alpha decay, 86 plus the alpha decay, which is your helium 42. It's charged alpha, right? So the value of alpha was not given in the question. If you notice, the mass of alpha is unknown, but you have to memorize this. Okay, U, this is atomic mass unit. If you calculate this, what you will get is 4.87 million electron volts. So you have found out the Q value of the reaction. Okay, so when you find the Q value is not of alpha particle, it is for the nuclear reaction. In the second part, if you notice, we have to calculate the kinetic energy of the alpha particle, right? So I already told you in the previous topic we did that the kinetic energy can be found out very easily once you know the value of the Q. So if you remember, it was Q is equal to the kinetic energy of the alpha particle, and this was to be written as m alpha divided by mr plus 1, right? We have found out this, put the value, we have to find this quantity. Okay, so if you put 4.87 is equal to kinetic energy of alpha particle, and you know the mass of alpha particle is known to you, right? And this is again Rn. Okay, both the quantities are daughters, and put the value of m alpha again. This is 4.002603 divided by mass of Rn, which is 222.01750 plus 1. Solve this equation and find the value of k alpha. Doing everything here. So kinetic energy of alpha particle will be 4.78 million electron volts. Do you see that most of the Q value, which is the energy released in this reaction, was received by the alpha particle, and the balance energy will be received by the Rn, which is the main daughter nucleus, the balance energy, right? Because it's very heavy and the initial momentum was zero. So this is the way you need to solve these problems, but first build your concepts. Don't look at solutions directly. You will learn nothing from them. Learn the basics first, as if you have, if you start seeing the solution, you will not understand anything. It is better to first go through the whole process of learning and then see the solutions. Otherwise, this is a futile effort. So thank you very much for your time, and wait for my next video. Thank you very much.